So with this under our belt, let's return to the vectors u1 and u2 from our earlier example. So in terms of our proposition, every two-dimensional vector can be written as u1 dotted with that two-dimensional vector b divided by the norm of u1 squared times u1 plus u2 dotted with b divided by the norm of u2 squared times u2. Something to note here is these denominators do not depend on the vector b. If we modify our vectors by taking v1 to be 1 over the norm of u1 times u1, and v2 to be 1 over the norm of u2 times u2, then we get two new vectors that are now unit vectors, and we can check that these unit vectors are still orthogonal to one another. So we observe that if we take our representation of b in terms of the orthogonal basis, u1 and u2, we can redistribute the two norms. We can rewrite this expression as v1 dotted with b times the vector v1 plus v2 dotted with b times the vector v2. Since the set C with the two elements v1 and v2 is an orthogonal set, it is also a basis for R2. This tells us that the representation of b as v1.b times v1 plus v2.b times v2 is unique. So while this may seem like a strange thing to do, this does lead us somewhere interesting if we're willing to shift our perspective. First, we'll think about this linear combination that we've written down as the result of a matrix vector multiplication. The two scalars, v1.b and v2.b, will form our vector. The matrix by which we will multiply this vector will have columns v1 and v2. Now, if we think about the column vector with the weights of our linear combination as its coordinates, we can think about this vector as b expressed in the coordinates corresponding to c, and we'll call the matrix Q. This tells us that the matrix Q, unsurprisingly, is the one that takes our representation of b in the coordinates for the basis c and converts back to the standard coordinates. If we think about the dot product, v1.b, as v1 transpose times b, and v2.b as v2 transpose times b, then we can split our vector as the matrix product. v1 transpose is the first row, and v2 transpose is the second row, multiplied by the vector b. And we can recognize this matrix as Q transpose. So we can express b as Q times Q transpose b, where Q has the columns v1 and v2, our two unit vectors, which form an orthogonal basis. We can think about this as telling us that we can convert between the basis C and the basis E using these two matrices Q and Q transpose. Putting all of this together, the fact that this works for every single vector in R2 is actually enough to conclude that Q transpose is the inverse of Q, so that Q times Q transpose is the identity. And this sort of behavior is very important enough to deserve its own name. An orthogonal basis consisting of unit vectors is called an orthonormal basis. And a square matrix whose columns form an orthonormal basis is called, confusingly, an orthogonal matrix. And what we have observed is that when we have an orthogonal matrix, the inverse of that matrix is its transpose. So, of course, the standard example to keep in mind for an orthonormal basis is one that's very familiar. It's the standard basis. Each and every one of the vectors EI has norm 1, making it a unit vector. And of course, they are all orthogonal to one another, so they make a nice orthonormal basis. So in the next video, we'll put our observations to good use, thinking about the problem of approximating vectors.